almost a museum. Carly's father was an avid collector, and if you were in that home, you might see a huge display of artifacts that came from here. Bird points, batates, manos. This is called Indian Springs, and there are springs, obviously one of the big attractions for a settlement. In fact, Carly, am I right? This was one of the campgrounds out here. A lot of your stuff has come from
this area. This is a wonderful spot.
You still have the bear trap in there?
We sure do.
They've got a bear trap. The jaws are.
Oh man!
Gosh. I bet it weighs 100, 200 pounds, or
Well,
I don't know.
It takes 2 men over 200 pounds, 2 hours to set it with clamps. It's a big thing. The teeth on it are like this.
Yeah. What kind of Indian was living here?
We had the Cheyenne, the Comanche, the Ute, the Apache, the Arapaho, and the Fischer drifted through. But the Fischer were nomadic. And they don't know if we were a trade area because I find Calf Creek, and they're really only out of Arkansas area. So they don't know if we were a trade, but I've got a lot of the natural clay that the Utes were pottery makers, and they never really made points. So they trade pots for points, and that's how the Utes got it. But they don't know if it was wintering here because our winters are mild, and we had the water, or if we were like a trade area.
They came out.
Yeah, I charged.
Right. They came out to use the restroom. You know why they came here. Incidentally, you know, you can sometimes find the teepee rings not by, you know, running around looking for bird points or looking for rocks in a circle and stuff like that, but by looking for circles of cheatgrass. Because the cheatgrasses come in to these heavily impacted interiors of teepees, like out on Teepee Buttes in eastern El Paso County. I was up there with a class one day, and I looked around and I said, gee, there are 3 circles of cheatgrass. What on earth are 3 circles of cheatgrass going up here? And we started looking around, and then we found where the rocks had been put at the base of the teepee poles, and we found 3 Pawnee Indian teepee rings up there based on the cheatgrass, which of course came in to a disturbed area, but it had been so disturbed that the cheatgrass, which came in from Eurasia much later on, was able to grow in areas like that. So often the botanist can tell you about Indian sites long before the archaeologists can, because the plant taxonomist is very sensitive to changes in vegetation that tell us about human impact in the past.
What's the significance of batates and manos in here? I usually would put them four corners.
Well, they must be grinding gamble acorns, which are sweet enough.
But with what culture might they be associated with? They just seem.
I don't know, because they,
If you're wondering where you are in the local rock column, lots
in Colorado.
lots of feldspar, lots of quartz grains, coarse angular particles. See the mica flakes in there? What do you think this might be, based on what you know in Colorado? Mexican crabs. Well, but it's a sediment. So Sawatch? Sawatch is almost a pure quartz sand. This is just loaded with mica flakes, feldspar, short transport of granite, weathered granite. Trying. You're getting warm.
Yeah.
Move down one notch. Thank you. Yeah, here are the Ancestral Rockies again. We're getting near the south end of the fountain red beds. The old alluvial fan stuff we saw at Balance Rock yesterday. You remember we stood there in the middle of that whole pile of debris that was shed from the Ancestral Rockies. There's the Dakota over there. We're obviously way down below the Dakota now. It's above us. Okay, just to get you oriented then. Over this point. Now, keep looking. Keep your eyes open. It's now 12:30,
Too late
and
for lunch.
I think you can find some shade or take the sun. And once you're through, we're going to, don't walk on the quarry floor, please. Very, very delicate. But I'm going to do most of my talking over there. But I think maybe a lunch break right now would be appropriate. Anybody disagree with that?
Also,
Shoot 'em
remember that we are in the Southwest, and there's a new oak in here that doesn't occur as far north as the Garden of the Gods. It's got a little tiny leaf like that, and nobody knows exactly what it is. They think it may be a hybrid between several of the southwestern oaks. I thought it was Quercus undulatus, wavy-leafed oak, but it's right back along it. It's a very short oak. It's about that tall. And I've not seen it this far north before. I've seen it at the Royal Gorge, but this is pretty unusual. And there's one of those southwestern oaks. It may be related to the one in Mesa Verde, the one down in Fort Union, New Mexico, but it's coming up north along the bottom of the valley, heading north. A little probably Quercus undulatus or some subspecies or species.
Well, enjoy this particular area and this particular subject. It all really started over 55, 60 years ago when I was reading my first geology book, written by Chamberlain and Salisbury. I could still almost recognize the page this statement was on. I was reading the chapter on the Ordovician period, and in that chapter there's a statement that the oldest vertebrates, record of the oldest vertebrates known anywhere in the world was found in Colorado near Canyon City. And this book went on to say that these early vertebrates were jawless fish, that the skeleton that they were evolving was external rather than internal within the body. In other words, it was in the form of armor plate on the outside. It was bone, calcium phosphate, had all the characteristics of bone, but it was not an internal skeleton as it first evolved. Well, after undergraduate work, I ended up later in graduate school in Boulder, and paleontology is my special interest. All my life I've worked with invertebrates, meaning animals without backbones. I know nothing about dinosaurs or mammals. That's not my field. But more technically, I'm a micropaleontologist. My doctoral study was devoted entirely to little tiny protozoan animals called foraminifera that secrete a shell. When they die, their remains settle down on the seafloor. And as a thesis project, I took on a study of the Benton and Niobrara formations in Colorado. I started up at the Wyoming line, went down to New Mexico, east out to the plains, west into the park areas, and described many new species and genera and so on of these little micro critters. That's where my main interest was. When I started teaching at Colorado College many years ago, fairly early in my teaching career, I picked up a Canyon City newspaper, and there was a picture of what was supposed to be a trilobite that had been found in the Cretaceous of Canyon City. And I said, oh my God, you know, if anybody's got a trilobite in the Cretaceous, they're going to make history. Well, it's Carly's father who had found this, and a local high school teacher had identified it as a trilobite. I tore down here to get a look at it, and what he had found was a palm leaf. It was the center of the palm with the venation coming out, and it looked just like the axial lobe of a trilobite. In fact, right today it's on display in the Canyon City Museum and labeled a trilobite, but it really isn't. It's a palm leaf. Well, that's how I met Carly's father. Then in the interim, after that first meeting of Mr. Thorson, Carly's sister was attending school at Boulder, and her dad had found some of these amazing rocks of which they built their home. And her sister took these up to John Cronick, who's the paleontologist at Boulder, and John took a look at them and he says, well, they're just some markings on the rock, doesn't mean anything. So she brought them home and was pretty discouraged. And about that time, the Mineral Society had a field trip going down here, and a local school teacher was on that trip, and she picked up a sample that had some very interesting markings on it. She called me, and my interest perked up. Where'd you get it? You know, well, down on the Indian Springs Ranch. So I tore down here and found it was Benny Thorson. And that started a friendship that spanned a good many years. When I got in here, I guess I just about went into orbit when I realized that this was the Ordovician. This was the unit for which the early vertebrates were reported by Walcott back in the 1880s. And in all the work that has been done on this formation, no one has ever found the body of the ostracoderm. There is in the National Museum a segment of the posterior end, which I have illustrated in this diagram here. This is how much of a dorsal imprint of an ostracoderm is actually known, of this genus Astraspis anyway. That's the only body fossil, but Mr. Thorson found this part here, part of the tail portion, and it's a silicified specimen with the imprint or the actual replaced plates, which are the diagnostic feature of the ostracoderm. Now, everybody has argued over what was the habitat of the early vertebrate. Was it saltwater? Was it freshwater? European anatomists, geologists have one opinion. They think freshwater. Alfred Romer at the University of Chicago argued for years for saltwater based on the structure of the vertebrate kidney. I'm not enough of an anatomist to go on and explain this, but the arguments ranged on whether these things were occurring over in Scotland in rocks of freshwater origin, whereas here the implication was saltwater, because there are trilobites in here, there are lingulate brachiopods, there are some clams, and they all are forms that we associate with the saltwater environment. Well, I started working in here and was suddenly dumped into the field I knew nothing about, the subject called ichnology. And ichnology comes from the Greek word ichnos, which means trace of or record of. The Germans call this Lebensspuren, the trace of ancient life. So these things are either Lebensspuren if you're a German, or if you're American, we call them traces. And by trace we mean the indirect evidence of life of the geologic past. Not the body fossil, but either walking imprints. Those dinosaur tracks you saw this morning are a trace fossil. They're not a body fossil. Well, in here, Mr. Thorson first handed me this thing, and I thought, my God, what in the world is that? I don't have the faintest idea. And I realized that it showed organization, it suggested organic activity, but I was totally ignorant in the field of ichnology, so I had to start reading like mad. Believe me, I burned many a midnight bulb getting journals in German, journals in French. A lot of this work had been done in Europe. It was a fairly new study here in the United States, so I had to educate myself first in foreign journals and then get busy on what was in print here in the United States. Well, this thing I couldn't figure out for the longest time, so I put it aside, and then we began finding beautiful things like this. And what you're looking at here is a ripple mark. You can see the cross-section of the ripple here. Very fine-grained sand. And here, if you watch my finger, are imprints of a swimming leg with a claw on the end of it there. You can see every hair on the leg where it dragged on the ripple. You can see the push mark there to tell the animal is moving in this direction. You can determine direction of locomotion. With the claw over here, you know the axis of the body had to be over here. So you start looking at things like that, and I would end up at night lying on the carpet and beginning to move my arms like a damn trilobite or something, trying to imagine what the limb pattern of locomotion was that was responsible for these unusual patterns. I took this one up to Reuben Ross at the Federal Center in Denver, and he's a trilobite specialist, and Rube said, he said, I'll bet you've got a resting site of a giant trilobite there. It's called Russo Ficus. The name doesn't mean anything, but that's a generic name that was given to this thing many years ago. Well, what you're looking at is the upside down, this is the filling of the burrow that was excavated out by a trilobite who had to have a body about that long. Wow. Now at this point, we had never seen a trilobite in the Harding any bigger than about ½ an inch. In the University of Oklahoma field camp, when they were out here in their museum, there's a paper written on this. There's a little pygidium and a part of the axial lobe of a very tiny trilobite, and it's the only known body fossil record of a trilobite that I'm aware of. I think Walcott maybe mentions they were here, but there are none in the National Museum, and there's this one in Oklahoma. Well, Carly's father began finding them up here in the shale above where we're standing. He found mostly these little tiny ones, so it was a little difficult for me to jump from these little tiny ones in the shale to these apparently giant ones that were recorded in this coarse sandstone. Well, this study went on for I don't know how many years. I'd come in here summers, I'd come in here weekends. I'd hike up these hills, Mr. Thorson with me, and we'd have a great big old pack, and we'd haul back all this stuff, and I'd haul it back to the campus, and I'd work on it. And I kept trying to correspond with other people who had worked on similar things, and I gradually put together this paper. And I had a former student who was a pretty good artist to do the drawings, you know, of the way I was interpreting the locomotion of these animals. And it ended up that we have here the earliest record of horseshoe crabs that I know of any place in the world. Before this study, the oldest horseshoe crab was thought to be Devonian. This is Ordovician. This is 450 million years old. And the way we know the horseshoe crabs are here is that the horseshoe crab is a chelicerate arthropod, which means they are an arthropod that have pincers on the end of the legs. And we've got specimens here that beautifully show the bifid chelate termination of the limbs, such as looking at them upside down. Here's the pusher foot, yeah, and there's the chelate walking leg there. It's got the pincer on the end of it there. Well, from that we found resting sites. Here's the horseshoe-shaped trace, the underside of the carapace of a horseshoe crab. And here he is coming in for a landing. You can see him just zooming in on the seafloor and the skid marks of the two prongs on the side of the cephalon there. Then you see his walking legs beginning to take off where he starts getting into orbit there. So that began to be interesting when you find that you have a record now of extremely early horseshoe crab existence here on the planet. The next big discovery was the walking trace of a scorpion. And a girl in the summer field class, here's the rock that she found right there, a beautiful walking trace with the drag mark of the telson, the stinger, and you can see how it swings back and forth as the scorpion is moving forward. If that was horseshoe crab, the tail is rigid, it would leave just a simple drag mark, but here you see the lateral motion, which argues that this has to be scorpionid. These are found in the Lyons sandstone I told you up in Lyons, Colorado. They're named Helcura. This one I named Paleohelcura, meaning the ancient trace of the scorpion. So we added scorpions now, which were previously known from Scotland, from rocks of, I think maybe Silurian, Devonian, somewhere in there. This pushes them back still earlier now to the Middle Ordovician. Well, this thing kept developing and developing, and I finally ended up, Mr. Thorson handed this to me one day. Here's a zigzag trace with punch marks on the end of it. And under a microscope, I could see the actual imprints of the rostrum, which is the nose of the astragoderm. And the star-shaped plate imprint convinced me that that was the feeding trace. And so I reproduced in this diagram. These were fish that had no fins, so they're polywog shaped. So obviously to locomote, they'd have to swing the tail laterally, which would mean the feeding trace would zigzag as it does, you know, in the actual specimen. So I then dreamed up a name, Agnathicnus fossor, the jawless fish, fossor, the burrower, ichnus, the trace of. I've given, you know, names to these so that these become type specimens. They're on deposit in the University of Colorado Museum. Well, if you looked at the footnote here, you'll discover that I went over to Australia in 1976, August, and presented this information at the International Geological Congress, which was meeting in Sydney. They meet every 4 years someplace in the world. So I had a great time. taking this information over to Sydney and making it public then. In the interim, we were fortunate through Carly's parents' effort and concerned citizens to get some protection here, and that plaque up there will indicate that this is now recognized as a national landmark. So why don't we remember, we're not collecting here. This is an area that is we're trying to preserve. Pick up anything and ask about it, but the rocks then become like this, what we call, you know what a leverite is?
Lever right there.
Yeah, lever right there. Yeah, that's a leverite. So we'll recognize things today as leverites. And don't walk on the quarry floor, but let's go on up there and see what we can see exposed.
Kevin, he doesn't.
Colorado in general was on the equator. Yeah, Colorado was in an equatorial position in Ordovician time. By plate motion, we have moved north now to our present latitude of 30, 38, 39 degrees. But back then, sitting about on the equator, so the climate would have been quite different from today, obviously. Secondly, at that time, the moon was a lot closer to the Earth. The moon, by precession, has moved out. Now, what does that mean about physical process at that time? The tides.
Tides.
Wow, yeah.
Big high tide.
Big high tides. And next, in the Ordovician, there were no plants on the surface of the Earth. So try and imagine this area now, closer to the moon, sitting on the equator, no plant cover on the land, life evolving like mad in the oceans, in the shallow seas. And here we are sitting on what I interpret as the mouth of a river. This is an estuary environment that we're looking at here. In this paper, I had this girl draw this section that shows what we call the flow regimes, technical name for that, showing the ancient channel here cut into the Manitou. The Manitou is right below us, and there's an erosional channel in which this material was deposited. And we start out with this fairly coarse basal sand, in which that huge trilobite trace I showed you was in, overlain as sea level rose. What was, formerly the channel of the stream is now overlain by finer grained sediments, and finally by shales. We get shale in the middle part of the section, and you're seeing here the effect of some change of sea level during the Middle Ordovician. So what does this mean in terms of vertebrate evolution? It doesn't really solve the problem of whether it was freshwater or saltwater, but these things are certainly in the estuary, which is a mixed saltwater freshwater habitat. And if I interpret this thing correctly, that's the environment in which they were living, these shallow lagoons, estuaries, along the base of some remnant of a Precambrian mountain block here. And where we find the conglomerates out here that are just solid plates of fish. If we have time, I'll show you those this afternoon. I think those are the post-mortem transport from these lagoons out into the open sea, caused by, the tidal drain of these lagoons and estuaries. In here, in the shales, a marvelous record of conodonts. You probably never heard of a conodont. But believe me, if you get a microscope and sift some of this shale and start looking, that these beautiful jaw structures with cone-shaped teeth. Conodonts have been known for over 100 years, but nobody knows for sure the animal to which they belong. I remember 20 years ago at the Field Museum in Chicago, somebody made headlines in newspapers around the world, announcing that he had discovered the conodont-bearing animal. Oh, everybody got all excited, wanted to see his specimen, and the final conclusion was he had found the animal that ate the conodont-bearing animal. That poor guy went down. He went down in smoke after that report. Well, anyway, I gave Carly's dad a microscope and turned him loose, and he became a pretty good micropaleontologist. I'd come down down here, and he'd have these. He was using one of her mother's nylon stockings for a sieve, and he was cooking on the kitchen stove and cooking out these conodonts, and he had the darndest collection of them that used to be out on the table there in their living room. So Mr. Thorson became one, a marvelous field collector, and two, a darn good amateur paleontologist. Well, I don't know what I can tell you more specifically. As I say, the light is terrible right now to see an awful lot. But if you want to kind of walk around and keep looking here and yell if there's something that you're particularly curious about, I'll try and answer it for you. Bill, what are these? I'm sorry. What are these? Look like hoof prints? Yeah. If you look at that stuff under a microscope, there's a lot of broken up lingula brachipod shell debris. These are very simple. They're still living in San Francisco Bay in California. They are a bivalve, a two-valve animal with a fleshy stem that anchor on the seafloor. And that's mostly busted up lingula shell material in there, plus conodonts. And I think they're just little erosional scours in the sand where we see, you know, some of the coarser fraction there that's being exposed. They're not traces, they're more a feature of erosion.
Yeah, a couple of footnotes to what Bill said. I'm a vertebrate zoologist, while Bill is an invertebrate paleontologist, so I look at things slightly differently. But the vertebrate zoologists are always interested in the origin of vertebrates. Where did vertebrates come from? And there are a lot of hypotheses, but one of the hypotheses that lasted for a long time ties right in with what Bill was saying at lunchtime. One of the hypotheses is that because people kind of vaguely understood what an ostracoderm looked like, they looked kind of like a horseshoe crab, that vertebrates, ostracoderms being the earliest major vertebrates, evolved from horseshoe crabs because of the similarity in appearance. Nothing else is very similar. That's an interesting sidelight. On the matter of the kidney that Bill touched upon briefly, we're very interested in just what kind of a kidney these early animals had, because freshwater fish have kidneys that prevent water from getting into their system. In other words, they have pumps that pump the water out of their bodies because they're in a freshwater environment, and they might have a tendency to absorb fresh water by osmosis, and so they have pumping kidneys. They have big filtering units to get rid of all the fresh water. Animals that live in salt water don't have those kind. They have very reduced kidneys because they want to save water. They don't want to pump it out. They want to save water because they're in a marine environment where there's a lot of salt. Well, it just so happens freshwater fish, the higher fish like the bass and the perch, have very good filtering units, and they're pumping out fresh water to maintain a balance between the body and the fresh water in which they live. Sharks, on the other hand, which are more primitive, but still more advanced than ostracoderms, sharks have a filtering kidney system which suggests that they evolved in fresh water because they have to retain their water in a different way. So they have very small filtering units. Sharks have very small filtering units to keep the fresh water in their bodies from escaping out into the ocean and diluting the ocean. So the vertebrate zoologist is always asking the paleontologist, tell us what kind of kidney the ostracoderm has, because that will tell us whether, in view of the fact that sharks appear to have evolved in freshwater, whether the earliest vertebrates evolved in freshwater or saltwater, and then you wouldn't tell us.
That's still
I was sitting there on the edge of that cactus waiting for you to come up. So these are really, it's interesting how all these things tie together, and newer finds may begin to answer these kinds of intriguing problems.
Charles Wolcott, director of the United States Survey, who discovered these in 1880, the actual, the plates from the ostracoderm. We can maybe find some upslope here. He thin-sectioned those, looked at them under a microscope, and the International Geological Congress of 1880 something or other came here to the United States, and they went right to Wolcott's quarry site over here, the Harding type locality, and all these geologists from Europe. He published his paper on the ostracoderms in the Geological Society of America Bulletin, and those people stood there and just shook their heads, and they said, you got the rock column upside down. This stuff can't be Ordovician. They were so convinced because over in Scotland, where previously in the Silurian section there were ostracoderms, and they were thought to be the oldest then. But these European geologists left here, what I've read, firmly convinced that Walcott had screwed the whole thing up. The section was folded and upside down, and that he wasn't in the Ordovician. I think since then anatomists have never disputed the bone structure of these plates. Bob Dennison at Field Museum worked a lifetime on these. I went many times to see him there in Chicago, and he's probably done the best histological work, thin section morphology of this thing than any other person. And he's actually found calcified cartilage elements in them. So cartilage had been invented by Middle Ordovician time. What's known about the kidney? Nothing. You see the soft parts, you're not going to get preservation of those.
How about kidney stones?
Well, we might get a kidney stone. Maybe a gallbladder stone or something. Questions from anyone? Yeah.
Yeah, I understand, and I think everybody else, how the fossil beds, how those were formed. Why did this mud make traces of the fossils? Like what happened on top of it?
Okay, you've got to look right above here, and you see the red shale coming in here. So if this is a ripple-marked surface, close to sea level, low tide, this surface could be exposed, minor change in the regimen of the stream and the level of the sea. This could be somewhat baked out in the sun, enough to solidify the surface over which these things have been walking. Then have some rain up drainage that would wash mud in rather than sand, and you put layers of mud over this surface. The stage is then set for preservation. It's one of those rare events like we saw at Florissant where things just clicked right with the eruption of the volcano and so on. This is what we call a facies, a part of the harding that is not preserved elsewhere in the state. Elsewhere in the state, this unit is missing. This is why this is so. Here's this unique estuarine record of that part of that formation. Just a week ago, I had a lady in Beulah, Colorado. I don't really know where Beulah is, but she heard me speak on this subject to the Historical Society in Canyon City a year ago. And she said, you know, I think I've got a fossil trilobite at home. And I said, well, great, I'd love to see it. Was it found around Beulah? And she said, yeah. Well, I said I'd get down last summer, and I got busy teaching, and I never got there. 2 weeks ago, she mailed me photographs of it. And I just about dropped because she had a photograph of one of these huge Russo Ficus, the resting site. And there is harding down there, but she has discovered now another little patch of this, apparently this same part. So I wrote her right back, and I'm going to see her the first week in August when I'm through here. But she said she went back with the boy who found it. She knows right in the creek where it's picked up, and obviously it's come from an outcrop above there, so I'll be up there looking in August. But that's the only other thing I've heard of where we get this part of the harding formation.
Then this is, you mentioned, you know, like in the alphabet
Yeah.
bed. So is this like the alphabet?
No, this is below. The alpha and beta are the two sands above us.
Oh, okay.
These real fine-grained sands that this one.
Okay, for the,
Yeah.
yeah, for the,
Yeah, these are the real marvelous traces, and
they're a little higher.
all right up
in
the slope
here.
here. Yeah.
Okay.
That's the sandstone. That's the sandstone.
There's some
Well, the harding sandstone, yeah.
scales.
Yeah, there's
I could be
some
wrong.
shale that's infiltrated in the harding.
Well,
So what do we got?
yeah, you've got some bony fragments there, Carly. I can see the bluish phosphate. Yeah. They're not clear enough, you know, to say whether it's Astraspis or Erypticius, but
Make it, we'll move, and you can have the shady spot.
well, I think you're beginning to learn that geologists, paleontologists are pretty weird people.
Speak for yourself.
Well, we'll include ecologists also. When you get into this field of ichnology, you begin to get a kink in your neck because you learn that the undersides of rocks are more interesting than the top. And I walk along here, you know, looking up under all these ledges because this is the coarse sand now in which those giant Trilobite burrows were forming. I don't know that we can recognize any here right now, but look on the undersides and you might, there used to be some evidence here, but I've forgotten where they are. This is the rock from which they came. Now do you see a change in rock type from here to here? All of this white stuff in here is chert. And chert is a form of flint. You think you spot some over there?
We're admiring the cactus.
Oh, well, that's permissible. We won't object to that. Do you see a little fold in here? Look at this little anticline right here.
Now this still Harding?
This is Manitou, this is Harding. This is lower Ordovician, this is middle Ordovician. We're at the contact now, the base of the Harding Formation.
Explain what chert is?
It's a form of flint. It's SiO2, silicon dioxide. In here, it's been, you know, Carly mentioned, and I did, there are a lot of artifacts in here that here to the north starts pushing all this sand out into a lagoon or an estuary. And it's in this sand, in the basal channel sands of that old stream, that these trilobites are working their way up drainage and burrowing down and then mud washing in, you know, or sand washing in to fill those burrows. So we're at the base of the Harding here. You saw the top as we started up the trail where the fountain and Harding were in contact. Several of you have asked about metamorphic rocks. We passed a few in the channel here that are washing out of the high ridge to the east of us here. There are gneisses, G-N-E-I-S-S, very well exposed in the next canyon onto the west. That canyon is cut into the basement rocks there.
Never been written up in the National Geographic, but the honey ants of the Garden of the Gods have been written up twice in major articles. What we got under there is the...
You're sure?
Can't believe it! We got the anthill of a honey ant. They're about that high. They're built just like a little volcano out of pebbles with a little hole about the size of a dime that goes straight down at the top. The honey ants are nocturnal. As some of you know, some of the lazy members lie beneath the surface of the ground on underside of slabs. They like the underside of things too. That's what I see when I look at the underside of slabs. I see these what we call repletes, these lazy honey ants who, and the busy ones run out here and get nectar from the trees, shrubs, and flowers, and they bring the nectar back.
Show it to us.
No. There actually is none there. But I mean, what can you talk about if you don't see any honey ant hills? And then they feed this nectar to these repletes, the lazy ones, and then the abdomen swells up until it gets about the size of a large garden pea. Some of you may have seen them. And then it ferments. Yeah, and when it gets black, that's a good year. I'll show you some slides tomorrow morning of that. And then I've eaten them and get intoxicated. Huh?
Are they kind of clear?
Yes.
And they're about
the
this
white
long?
ones. Yeah, they're round.
And they've got a black abdomen.
Are these the ants? No, actually, you never see them out on the surface of the ground. We may see them.
Only at night have I seen them.
Well, you may have, but the repletes never come
around
out.
the campfire.
No. Did any come up?
What a letdown.
That's what it is then.
Yeah.
I'm sure that's what it is.
Yeah, those are the famous honey ants. They occur, I think, they occur in Australia. They're not related, but we have ecological equivalents in Australia and in Africa.